So this is your chapter 50 out of the book on batteries. The main purpose of a battery, and the reason why we have a battery as big as we do, is to operate the starter motor. And so the starter motor like this draws more amperage than anything else on the car. If it wasn't for that starter motor, then we wouldn't need the big batteries that we have. And so since a primary purpose of the battery is to operate the starter motor, then when batteries fail, then we often end up with a condition on the car that the vehicle does not crank over. And so I always want to give some context as to the application of why we learn what we learn. And so then understanding at a deeper level what makes up a battery, how it works, why it works the way that it does, helps us diagnose problems with the batteries. And so some of the major functions we talked about, operating the starter motor is one of the primary functions of a battery. And so when the battery fails or we have problems with our battery, we are not able to crank the vehicle over. It does provide current to the ignition system during cranking. And so the reality of that statement is that the ignition system that we're talking about there is the ignition system that ignites the air-fuel mixture. The reality is the battery provides the electricity to all of the necessary components that are necessary during cranking to have an engine that will crank over and start up and run. So yes, it provides the electrical energy to the starter. It supplies electrical energy to the ignition system. We need to have spark to be able to start a motor. Modern vehicles have computers and a fuel system and a lot of other necessary electronics. Our computer controls that are necessary to be active during cranking, those will be powered up as well. And so that statement should be understood a little bit more generally, that during cranking, whatever is necessary to be in operation to have the engine fire up and run will be active. The things that are not necessary would be disabled. So a lot of you may notice like your radio will stop playing, or skip a beat during cranking because it's not a necessary device to have the engine start up and run. The priority during cranking is starting the car and being able to have an engine that fires up and runs in the end. The battery also acts as a voltage stabilizer. And so what I want you to understand from that is that on a DC system that we have on the car, the electrical energy for that car will begin and end with a battery. Yes, we have an alternator that supplies electricity, but it can only supply so much. The available electrical energy from the battery is far more than what an alternator could hope to put out. So a lot of these batteries are rated in cranking amps or cold cranking amps, and those are two different ratings. One is at a rating for a cold weather, and one is for warmer. But you'll see batteries, your average battery, 500 cold cranking amps. Alternators, 160 amps for a real high output one. A lot of your little Hondas and things like that, they may have an 80 amp alternator. So the battery has the capacity to produce a lot more electrical energy than anything else on the car, and it's one of the major draws of electricity in that regard. The electrical energy that left there wants to come back in that circuit to the battery. And so any high voltage, any irregular electrical activity that happens on a car, voltage spikes or surges or things like that, the battery will eat those and spit 12 volts out on the other side. And so the battery protects a lot of the other electrical devices, stabilizes that DC voltage at a certain level to protect other devices. Some devices, computers, sensitive electronics, if they got hit with real high voltage, then it could damage them. Well, the battery does protect those other electronic devices because any high voltage that's generated on the vehicle naturally is drawn back to the battery. And so that is a very important function. You may have, I'll bring it up now, but those of you that poke around on YouTube and watch YouTube videos and things like that, there's a test that had been around in the automotive industry before computers existed on cars. And one of those tests was to test, it was intended to test the charging system. And so while the vehicle was running, people would disconnect the battery while it was running, and if it stayed running, then that proved that the alternator was working and generating electricity. there are people that don't know that much about cars that are still espousing that as a valid test on a modern vehicle, and some of you may have even done that to your cars. I usually have a few people in the room that are like, oh yeah, I've done that before. The reality is that's a risk on a modern vehicle, because as electricity is moving through a circuit, it carries with it that electrical energy and that electrical pressure. Well, just because you disconnect a circuit, those electrons still want to try to flow, and so what tends to happen is they kind of pile up and stack up, and it'll produce this spike of high pressure that we would call a voltage spike. Well, they can be pretty high, 50 volts, 100 volts, 250 volts. And so when that happens, that high pressure has the ability to jump and arc circuits and things like that. Well, the battery is the natural draw that draws those high voltage spikes to it, and it will eat those and turn it into chemicals, which is what a battery does. Is it is a chemical way of making electricity. And so it'll eat that high voltage, but if we remove that battery from the equation, then high voltage can kind of go wherever it wants. And computers in cars have little devices that are called capacitors inside them, and they're kind of like a little mini battery. The difference between a battery and a capacitor is a capacitor stores electricity and a battery generates electricity, produces it. But a capacitor has a similar kind of draw like a battery, and so there's a risk that that high voltage may want to go to the capacitors that are inside sensitive electronics, computers. And so if it does, then it can bounce around in there and fry them or damage them. And so that test is that of disconnecting the battery on a running car was originated before we had computers on cars. It is not considered a valid test, and some of you may have seen people kind of promoting that test out on the internet. That is not a test that you would do on a modern vehicle. You can damage it. I had a customer that found that test on the internet and disconnected their battery on their little Volkswagen, and they fried a ton of modules. So when they disconnect the battery, the car died, and they're like, oh, my alternator must be bad. They hooked their battery back up and went to restart the car. It didn't start. They fried like 30 modules on that car, and it was a hugely expensive repair. And some of you that are out there are like, well, I've done that before and it didn't damage it. Well, you kind of, sometimes it won't, right? You get lucky, right? It may damage it. Maybe that electricity didn't go and damage anything. But what I'm telling you is it can. And so that's not a test that we want to do in the automotive industry anymore. There's a risk at damaging components and doing something like that. Plus, you also, if you're disconnecting your battery on a running car, it's going to arc. You might blow up the battery, right? It's not a very safe test to do either. So be careful what you read on the internet. There's a lot of stuff. The more you learn about automotive, the more you'll kind of pick up on some of the BS that's out there. And so that test is 50 years old plus. And even if you're like, well, I got an old hot rod, I could do it on mine, right? Do you not have a modern radio in it? You could fry your radio, right? If you got a nice flat screen radio LCD display or whatever, you got a nice screen on that radio, you could damage it in doing a test like that. And so I would never condone doing any of those tests like that. But our battery is our voltage stabilizer. It also provides electrical energy when the demands exceed the output ability of the charging system. And so most of you have seen this as well, that somebody's got a stereo system in their car and their subs hit, and then you see their lights dim out at night. So what happened there is the lights were brighter when the charging system was in operation. We're running 14 volts out of our charging system. When the subs hit, and the charging system couldn't keep up, then the voltage went down to battery voltage closer to your 12 volts, and then you saw their lights get dimmer as the subs hit because the battery was picking up the slack for that electrical energy to operate those subs. And so the battery will do that. If we ever exceed the output of our charging system that generates electricity mechanically on board the car, then the battery will pick up the slack and has the ability to do that. Then the battery also provides us a means for operating our accessories when the engine's not running. We can listen to the radio, we can roll the windows up and down and things like that. That's all on battery power there. So batteries don't actually store electricity. They store chemicals that we use to produce a chemical reaction to produce electricity. And so most of your automotive batteries are going to be a lead acid battery, that there will be two different metals in there. you'll have a lead peroxide and a sponge lead. So the lead peroxide is what we would consider our positive plate, and the sponge lead is the negative plate. So this is, by the way, our conventional theory and conventional understanding. And the truth of it is that when you do test batteries and when you see me in our electrical lab, you'll notice that I'm showing positive current coming from the positive side of the battery, because that is where the electrons come from. As it's labeled, the plus side is where the electrons come from. They return to the negative side. When you look at the materials that are inside there, the science behind that, the positive plates have an excess of electrons. And then our negative plates, labeled appropriately, sponge lead, kind of gives the idea that there's porous, there's holes, there's lacking material. They are the side that lacks electrons, and so that's where the electrons go to. And so then we have electrolyte. So two different metals, they're both lead, but one is a lead that has an excess of electrons, the other one is lacking electrons on our negative plate. Then our electrolyte is a mixture of acid and water. So it's sulfuric acid 36% and water 64%. And so that is our acid solution that we have, our electrolyte, inside the battery. And so the science behind this is that if you submerge or immerse two different metals in an acid solution, then a difference in pressure exists between them. We call that pressure voltage. So if I put two different metals in an acid solution, then that produces voltage or electrical pressure. And so that's the science behind what makes a battery work the way that it does. And so through the life of a battery, it's partially discharged and then recharged. So these batteries are rechargeable. If that chemical reaction gets depleted, it can be reversed to where we end up with a fully charged battery again. So in order to recharge a battery, it does take a higher external voltage. If you really want to nerd out and be curious, like, well, how does that work exactly, right? Go ask the physics department. That's beyond what I ever cared about. And so I know that higher voltage will reverse that chemical reaction. It takes 2 volts higher, which then explains why when our battery is in operation, we have 12.65 volts. And when we start the car, normal charging system voltage is 14.5 to 15.5 volts. So that happens to be 2 volts higher than battery voltage, even of a fully charged battery. And so then that is able to reverse the chemical reaction. It takes 2 volts higher to be able to reverse that chemical reaction. And so then we see and understand why the charging system has been designed the way that it has, as that supports the science behind this of what it takes to recharge these batteries and reverse the chemical reaction. So this is just a display of kind of the life cycle, if you will, of a battery, that when it's fully charged, we have those 2 different metals in an acid solution. So we know that on our positive plate, we've got our lead peroxide. On the negative plate is our sponge lead, and then on a fully charged battery, the acid solution will be 64% water, 36% sulfuric acid. When I hook up an electrical load to this battery, then it will start to discharge. And we'll have electrons leaving from our positive side of the battery and returning to the negative in that circle or circuit. And then that is going to then change that chemical reaction in the battery. And what ends up happening is that the acid starts to become more water and less acid, so we start to get that shift away from 36% sulfuric acid and 64% water to maybe 30% acid and 70% water, and then as it discharges further, then we've got 20% acid and 80% water, to the point that when it's fully discharged, then not only is the acid basically, or our electrolyte, 100% water, but as we have electrical material or electrons leaving our positive plate and depositing on the negative plate, then what happens to those plates is they start to become lead sulfate. To where when a battery is completely discharged, then our electrolyte solution is pure water. The 2 plates are identical now. They're lead sulfate and lead sulfate. And so now we've lost our scientific principle, right? The scientific principle that creates that electrical potential or pressure or voltage is that we have 2 different metals in an acid. Well, when a battery is completely dead, then we have 2 of the same metal in water. Well, that doesn't make electricity. The good news is it can be reversed. Higher voltage, 2 volts higher than what the battery voltage is, will start to reverse that chemical reaction. And so then you'll get material. How it does that exactly, I told you I'm not privy to. How does it move? Where does it move? But we know that will reset or recharge that battery to where we bring it back to a state where I have 2 different metals submerged in acid. And so that chemical reaction takes place on all fronts. The lead changes, the electrolyte changes in the battery as it depletes, so we can actually get an indication of the state of charge of a battery by just checking the electrolyte and seeing what its specific gravity, they call it. It has to do with density. Is the density supportive of being majority water, or is it supportive of being that acid and water mixture that we want? And based on that proportion, the density of that changes, and we can get an indication of what the state of charge is. Obviously, it's much easier just to check it with a voltmeter, right? So we just look on the 2 terminals of the battery and check it with a voltmeter, and we can indicate the state of charge of the battery there. Fully charged battery is 12.65 volts. And so in this case, with batteries, you may have heard the terminology when a battery is completely dead, or an indication of kind of the health of this battery. You'll hear technicians a lot of times refer to the battery chemistry by saying, oh, that battery is sulfated. They're referring to the chemistry in that point, because the plates of that battery turn into lead sulfate as it gets discharged. And the reality of that is, lead sulfate kind of wants to stay lead sulfate. It becomes a little more stable as a solid, as sulfate than it does in its ion form of lead peroxide or sponge lead. And so it becomes a little more stable, and it's harder to reverse the chemical reaction. So the reality is that batteries, as they're discharged and recharged, when they recharge and reverse that chemical reaction, the truth of it is that some of that lead will stay lead sulfate. So when we condemn a battery is when that battery can no longer produce half of what it's rated for. So if it's rated for 500 cold cranking amps and now it can only produce 250, then we are a glass half empty situation in that case, not a glass half full, that battery we would consider more than 50% bad. And so that's when you condemn these batteries. And so because now they would be considered unreliable, and that's the way that we test them. And so these lead acid batteries that you see in an automotive battery has a greater capacity because we're expecting it to be able to deplete, or we're expecting its efficiency to fall off as it discharges and recharges, and some of that lead stays lead sulfate. As that happens, lead sulfate is a higher resistance material, and so as it tries to reverse that chemical reaction, gets hit with that higher voltage from the charging system, because that lead sulfate is higher resistance, it starts to generate more heat as we try to recharge that battery, and it'll start to boil out their electrolyte. And so in the context of when techs usually will say, well, that battery is sulfated, they're usually wet and have a lot of corrosion over them, and that's a pretty good indication of the internal condition of that battery, that it's likely sulfated on the inside. Some of you may be curious about some of the other construction of batteries. We talk about it more in the electrical class at the college, the different materials that are used, but there's dry cell batteries or gel that you may have seen, the Optima batteries, or Duracell makes some, I'm sure other manufacturers do too, that they're not a lead acid battery, and they don't have they're not a wet battery in the sense that they've got a liquid electrolyte on the inside. They're typically gel in those cases. So the benefit of a battery like that, they're obviously more expensive, but they can be inverted and mounted upside down or turned on their side, and they don't tend to gas any harmful or even they don't gas as much flammable material or gas or hydrogen gas. And so you have those, and then there's also marine batteries. Marine batteries are typically lead acid, and the marine battery is not any different really than our automotive battery. It's still a lead acid battery. What they do is that you can tell the difference by the weight. If you pick up a battery like that, they're pretty heavy. And so all that they're doing is they're sacrificing more material to this kind of life cycle of this battery, that they put more lead in it to sacrifice to be able to turn into lead sulfate. These automotive batteries like this one, it is bad for this battery to be deep cycled. So what deep cycling is where we completely discharge it to where it is lead sulfate, and water. And that is harmful to a typical automotive battery. A marine battery is designed for that because what they do with that is it's no different than this automotive battery, still a lead acid battery, but they just put more material in there to sacrifice. When you deep cycle them and run them very completely dead, it's harder to bring that battery back to a full state of charge and reverse that chemical reaction. With a marine battery or deep cycle battery, that's still true of that battery. They just put more material in there to sacrifice to that process so that battery will stay functional for a longer period of time. So I want to talk a little bit about what's inside the automotive battery, and really any battery for that matter. What they end up doing is they've got a grid or framework that they attach material to. And so if it's going to be a positive plate, then they'll put the lead peroxide on there. If it's going to be a negative plate, they'll put the sponge lead. And so they build these plate groups that they strap and build a plate group for the positive plates and a plate group for the negative plates. And then they sandwich those together. And when they do, they put separators in between so that they when they sandwich it together, that the plates can't touch each other and short out. And so then once they build that whole unit together, then they've got an element. And so they'll place that element down in a cell in the battery. And so we've got this is just a demo battery that shows different cells of different capacities. So that's why on an automotive battery or a battery that would be in a car, all of these cells would be the same size. So this is a demo battery showing different amperage capacities and different varying amounts of plate material. When they get that element in a cell, in a battery, which you can see that this one has 6 cells, which a 12-volt battery would also have 6 cells. A 6-volt battery would be half of this and would have 3 cells. And so when they build it all together and they have a cell, when you submerge it then in the acid solution, then it creates a charge or that potential energy or electrical pressure that we've been talking about. Now, some of you may intuitively start to think, well, if you put water over that, wouldn't it short it out? And if you put tap water in it, then yes, it would. But distilled water or pure water actually does not conduct electricity, which is something that had kind of tripped me up for a while. I'm like, why? How does that not short it out when you fill it full of water? The pure water or distilled water does not conduct electricity, and so that does not short these out, which is why in doing your maintenance on batteries, it's important not to put tap water in them, because ultimately whatever impurities are in that water or other elements besides water are in that, they will produce somewhat of a chemical reaction and conduct electricity and ultimately hurt the capacity of that particular cell or that battery as a whole. And so we do want to top off batteries with distilled water. So once we get the element built, then it goes down in a cell. So this would be your element. We've got a negative plate group and a strap bonding all of those plates together, a positive plate group and strap. So you can see some of your grid and then your plate material on there. And then insulators go in between. And so when it's down in the battery, then we've got a cell. And then they connect those cells together to then combine the available voltage for this battery as a whole. And so we'll have a case on that battery. There's often a little area down below on your serviceable batteries for any sediment or material to fall down to. Some of your maintenance-free batteries that are not serviceable, that don't have caps on them like this where you can top off electrolyte level, will have a little hydrometer, a little plastic eye that indicates the state of charge or if that battery is no longer any good anymore. You have top post designs, and some will be side posts like what you see here. This is a combined top post and side post. So it's got side post terminals as well as top post terminals. It does have covers to pop, no hydrometer on it. When they don't have the covers on there, they're considered maintenance free. And so then they'll be sealed, and then that's often when they put the hydrometer on there, or like a charge indicator on these batteries. So case is plastic. How many of you have heard, or maybe your dad told you this, my dad told me this, that if you set a battery out on the ground, that it will cause it to go dead? My dad told me that. He was always big on like, hey, don't set that tractor battery down there. You got to put a block of wood under it, right? So otherwise the battery will go dead. Does plastic conduct electricity? No, right? This is a plastic case. It doesn't conduct electricity. So it is not true if you set this battery out on the ground that it will go dead. That is a story that has been retold and retold that's well over 100 years old. That was true for batteries back when they made the case of the battery out of wood. Anybody ever seen a wooden case battery these days? No. So I haven't. But that's a story that gets retold. It's kind of like there's a preacher story that they'll tell at church where they say, well, when mom cooks the Thanksgiving ham, then she always cuts the ends off of it, right? And then the daughter's learning from her mom. She's like, well, mom, how come we cut the ends off of this ham? As well, that's the way my mom did it. So she calls up her mom, like, hey, how come we cut the ends off of the ham? She says, oh, well, my mom did it that way. So they call the grandma. Well, how come we cut the ends off of the ham? Says, well, I had to cut the ends off of the ham because my pan wasn't big enough, right? But then it gets taught, right? If they had too small a pan, they had to cut the ends off of the ham so they would fit in the oven, right? So then then everybody cuts the ends off of the ham. That's kind of like the battery story. It gets retold, even though nowadays on a plastic case battery, it's not true. And so batteries setting out in the open like this will go dead anyways from the dust that collects. The dust will conduct electricity, so they'll go dead, whether sitting on a bench or sitting on the floor or whatever. But it doesn't matter in that case whether it's up on a bench or on the floor. If it gets dust on it, that can conduct electricity, or moisture on it, that would conduct electricity. But if it's a clean, dry battery, you can have it sitting there indefinitely and it's not going to go dead. Setting on the floor certainly won't make it go dead. However, setting on concrete for a wooden case battery, okay, that makes sense. So these battery cells, there's 6 of them in a 12-volt battery. They connect them in series. So they produce individually, each cell, 2.1 volts per cell. When we connect that in series, that adds up. 6 times 2.1 is 12.6, and ultimately fully charged becomes 12.65. And so it's 2.1 and some change, right? So connecting those cells in series adds that voltage up. If I were to take 2 12-volt batteries and hook them up in series, so I'd go positive to negative, right? That's series for our cells. If I took 2 12-volt batteries and didn't go positive to positive, that would stay 12 volts, but I went positive to negative, that would make 24 volts. More commonly, for trailer applications and travel trailers and motorhomes and things like that, they'll have a battery bank, or in golf carts or things like that, they'll have a battery bank. And if you take 2 6-volt batteries and you hook them up in series, that makes one giant 12-volt battery. And so that's an application for knowing this type of stuff. But in here, where the plate straps are connected together, positive, negative, then positive, negative, right? And so they'll be hooked up in series so that overall, terminal to terminal, all of these cells are connected up in series. That makes 12.6 volts overall. So understanding this construction also should have this diagnostic repercussion or understanding. That since the cells in this battery are connected in series, any battery as a whole is only as good as its weakest cell, because that current and electricity has to be combined in series. We know in a series circuit, if you break one spot in the series circuit, the whole circuit's dead. So if I have one cell that goes dead in this battery, the whole battery is junk. So, conventional versus maintenance-free batteries. This is a conventional battery here. This one is a maintenance-free battery. No serviceable caps. So this is a small, little, lawnmower or motorcycle battery, something like that. This is a conventional battery that does have caps that I can pop loose. So I can see the electrolyte level in the top of that battery. And the idea really when you're topping off batteries is just that we want to make sure that we fill the battery up till the electrolyte level is above the plates. So if I look down in a battery, I don't want to see the metal plates. I should see the electrolyte solution in there. And so the conventional battery is what we see up here. This is a conventional battery that has sediment chambers down in the bottom. This thing rattles around and bounces around, and that whatever material falls off can settle down in the bottom of this battery. What they do with a maintenance-free battery is that each one of the individual plates gets bagged. So they put a bag around each individual plate. Now, the reason for the sediment chambers in a conventional battery is that if that material breaks loose and falls off, it has the potential to be able to short out the battery, so they let it settle down in the bottom so that it can't short out the battery. If they bag each plate individually, then whatever material falls off has to stay with that plate. So it has no potential or opportunity to short out the battery, the plate, or against another plate, or short out that cell. So, because batteries are sold by group size has to do with the physical dimensions of a battery. The battery for any particular car, they made a certain size tray for that battery, and there's a certain group size battery that goes with that application. And so, this one is a group 24, this is a group 78 type battery. And so the group size for these batteries has to do with their height and their width and their height, their width, and their length. And so that will constitute a certain group size. If you've seen the little Honda batteries, they're like but they're super small, right? Kind of like this. Now it's about twice that size. But they have different group sizes of batteries. Maintenance-free battery, the idea, if I'm not going to have room to top off electrolyte, but yet I need to keep the same group size, then by bagging each one of these plates, they can get rid of the sediment chambers down in the bottom, lower that element down further in the cell, and leave room to put more electrolyte over the top of it. So the hope and the goal is that we can add enough electrolyte to that so that it will last the life of the battery and not require any topping off of electrolyte. That's what they do with a maintenance-free battery. Eliminate the sediment chambers, bag each one of the plates so that they can add more electrolyte and it doesn't need service. With the maintenance-free batteries, you typically see the plastic eye. Since I don't have the opportunity to pop the cell caps and look inside to see that it's full of electrolyte, then what they generally do is put a little hydrometer in there so we have at least some sort of an indicator on what the condition of that battery is on the inside.